we'll go ahead and get started with the last talk of today in the second session here from Peidong Yang, who will be telling us about semiconductor nanowires. The floor is yours.
Yes. Thank you. I want to start by thanking the foundation and Cassie for the invitation for this wonderful conference. So I'm going to talk about on some of the research we have been doing over the past maybe more than 2 decades now on the semiconductor nanowire. It's a very unique building block for the nanoscience. Let me start with this first slide. So we all know for the carbon, we can consider carbon in terms of the structure you can make out of it. You can see C60, carbon nanotube, and the graphene. And that's something you can consider it's sort of a 0D, 1D, 2D version of a building block from carbon. Okay. For the semiconductor itself, by now we also have these sort of 3 classes of different dimensional nanostructures, 0D, 1D, and 2D. Just a couple of weeks ago, the 0D version, that's just basically quantum dots, was awarded the Nobel Prize. Then the nanowire, semiconductor nanowire is just 1D version of this nanostructure. Then more recently, we also have lots of research on the 2D. Okay? For semiconductor itself, when we think about these different dimensionality, I think we mostly care about their density of states. Okay? And that will basically, the density of state change whether you are in the 0D version, which is electron is being confined in 3 dimensions. In 1D nanostructure, electron is confined in 2D. In 2D version, of course, electron is confined in 1 dimensional. Okay? And these different dimensional sort of confinement give you so-called different density of states. And fundamentally, by engineering the semiconductor with these different dimensionality, different size, you are changing the electronic structure. Therefore, you are changing their optical properties, their electronic properties. Okay? So I will walk you through actually the history of this development on these semiconductor nanowires. So when I talk about these, the nanowire growth, I normally will go back to this very relatively old Bell Lab work by Wagner. Okay? And this is, look at this, this is back in the 60s. Okay? Back then, Wagner at the Bell Lab is working on basically developing a growth methodology to grow ultra-pure silicon, germanium, bulk, single crystal, just like Steve mentioned during the noon talk. Okay? And at that time, basically, Wagner developed this so-called vapor, liquid, solid crystal growth methodology. Okay? And he's using this methodology to grow silicon, ultra-pure germanium. And you can see actually this, this image, basically the scale bar is the millimeter scale, right? It's a very big single crystal. And the so-called vapor, liquid, solid, you will see also some feature, this sort of semi-spherical particle that's in a chemical vapor deposition system at a high temperature, that's a liquid. Okay? And when people actually, when we're using this VLS methodology to grow these one-dimensional crystal, you have a vapor phase, for example, silane, germanium vapor, okay? And that's a vapor source. So this is liquid. Then the solid, so-called solid, is the single crystal of silicon and germanium. That's what we call it as VLS. Okay? So this is certainly goes back to a long, long time ago. Now, if we look back in that particular paper, you're already seeing, okay, these filaments here. Okay, you look at this scale bar. It's 300 nanometer. Okay, so back then, Wagner is already indicating this is transmission electron microscopy indicating one can make these nanoscopic filaments of silicon and germanium. Okay, and the VLS is basically demonstrated over that time. But of course, at that time, really nobody looking at these sort of unique optoelectronic properties of these semiconductors. Okay. Now, this is almost now, for me, it's almost 30 years ago. 30 years ago, I joined the Charles Lieber's group at Harvard. Okay, started my Ph.D. And this is my first sort of work on sort of inorganic nanowires. And this is also Charlie's first work on inorganic nanowires, because back then, almost everybody is working on carbon nanotube. Okay? And I started to do something interesting, something new, okay? And basically started this inorganic nanowires. You can see that these are some oxide nanowires where back then we use this as the sort of flux line pinning. It's in the high temperature superconductor. You use these linear sort of nanoscopic object to pin the flux line so that you can enhance the so-called critical current density, the current density you can carry without lose any sort of energy. Okay? So that's basically the first example from sort of my Harvard time, PhD time. And that actually leads into the sort of first example of using VLS methodology to grow these inorganic semiconductors like MgO, zinc oxide. Again, you can see back then, this is in my thesis, you can see this is a zinc oxide nanowire with liquid droplets on top. Of course, when we're imaging it, it's solid. Okay. And we made it back then, we basically made the definition. Of course, at very earlier days, we call them nanorod. Then the community, the field started to grow. People start calling them nano whiskers. Okay. Eventually, the community settled down with the nanowire name. Okay. But the definition here is essentially the cross-section of the semiconductor structure will be anywhere from 1 nanometer to a couple of 100 nanometers, then with huge aspect ratios. Okay? And that basically adds a building block itself that differentiates from these quantum dots. Okay? Quantum dots is three-dimensional confined. Therefore, you don't necessarily have this electron connection or electron transport property. Whereas for these one-dimensional objects, you can think about all sorts of transport, electron transport, thermal transport, which you will see later on when I talk about their physical properties. Okay? And that leads into the first sort of nanowire pattern back then in '96. Okay, you know, actually I listed here. That's in my second or third year of PhD. Charlie actually came to Welch conference, okay, almost 30 years ago. There's another, at that time, the Welch conference is called Chemistry at Nanometer Scale. Okay? And that's the first time Charlie talked about this inorganic nanowire work. So 30 years later, I'm talking about this sort of how this field is getting really bigger and bigger, and now there are many research groups working on this. Okay, okay. So I finished my PhD at Harvard. Spent maybe just very briefly 1 year at Santa Barbara with Galen Stuckey. Then back in '99, I started my independent career at Berkeley, and it's basically coming back to really with the entire group devoted in this area of VLS nanowire growth and their optoelectronic properties. And I think the first work we did is quite important. That basically underpins really for the first time, the growth mechanism, how we can have precise control in this one-dimensional nanostructure. That's the key. Before we having these precise control, we cannot talk about size-dependent properties. Okay, so that's the growth mechanism. We basically, that's my first graduate student, Yi-Ying Wu, now at Ohio State University. So this work actually we carried out at the time. Again, not so much on the Institute TM. We did this in the Institute TM in the molecular foundry. Actually, the older name is NSAN. At very high temperature, okay, 800 degrees in an Institute TM in the column. And we basically, during this stage, what we're doing is you sprinkle the TM grid with gold nanoparticle with different size. Then supply, actually, with the neighboring, actually, you generate germanium vapor by heating the grid. And that will basically essentially generate germanium vapor locally around the gold nanoparticle. Okay? So now if we look at this is the key. Okay? Look at the phase diagram of this so-called the eutectic binary system. Gold is our sort of a nucleation site. Okay, that's our liquid droplets in this VLS name. Okay. Then germanium is supplied as vapor into in this case, into the TM column. And that will basically start to mix at 800 degrees. Okay? So if you look at this phase diagram at 800 degrees, when you're adding more and more germanium vapor, the germanium will alloy with gold, and this isothermal line pushes this into this liquid state. Okay? That's the phase diagram will tell you. You will see a liquid droplets formation. But once you cross this biphasic region, it's telling you that you are going to see two things. One is liquid. Okay? This is the liquid line. Okay? Another one is single crystal germanium. Okay? And that's exactly at the time we're seeing here. So you are seeing at, again, high temperature. Initially, pure gold is solid. Once you start to alloy with germanium, you start to see it sort of becoming a liquid puddle on a TM grid. Okay? And this is a gold germanium liquid puddle. Then you keep adding vapor into the system. Okay? This is VLS. Eventually, you see this thing pop. Okay? You will see many of these things pop instantly. What that is telling you, the popping of this sort of dark contrast and a light contrast, that's the biphasic region. It's telling you we're getting into this biphasic region. And this dark spots, that's our gold germanium liquid. Okay? And that certainly gold is heavy, so it appears as dark. And the light spots here, that's pure germanium. Okay, so you are seeing a baby germanium nanocrystal starting coming out. And once you establish this liquid-solid interface, the rest is basically promoting one-dimensional crystal growth. More vapor goes in. You will first go into the liquid surface because the sticking coefficient is higher. Then it pushes out as a sort of towards one dimension. Okay? So this basically is telling us the liquid-solid interface generated at this high temperature is the fundamental mechanism for one-dimensional crystal growth. It has nothing to do with the crystal structure we're making. Silicon is an FCC structure, a cubic crystal structure. Usually, thermodynamically, it would not prefer a sort of one-dimensional crystal growth. Okay? So this basically telling you, once you have this liquid-solid interface, you can make one-dimensional crystal structures. And that actually established the fundamental mechanism. Later on, of course, many research groups use this VLS to grow almost any semiconductor, silicon, germanium, 2635, almost anything that you can utilize, as long as you can find the right sort of eutectic phase diagram. Okay? And that also allows us to do a basic major sort of control in terms of, first of all, size control. Okay? This is very important in the nanoscience. You need to get into quantum confined region. This is fairly easy to do the size control once you understand the mechanism, because the size of these nanowires is controlled by the particle size you put in. Okay? We heard a lot about these nanoparticle synthesis. You can pretty much make a very monodispersed metal nanoparticle and go into your CVD system and grow these, in this case, is silicon nanowires. You can see this particular one is down to actually sub-2 nanometer scale. Okay? And that some labs basically can use this to make transistor as well. Size control, orientation control, you can make vertical arrays, horizontal sort of bridges, and those are all controlled by where you are placing these catalysts. You can, if you call these metal nanoparticle as the sort of one-dimensional crystal growth catalyzer. Okay? And positional control, you can, later on you will see this again. We can basically position these individual nanowires by precisely placed on top of interconnected electrodes. Okay? And this is very important for us later on when we talk about photoelectrochemistry, single nanowire-based photoelectrochemistry on individual wires, because everything now you can wired, you can basically measure in electron transport, measure in optical absorption on a single nanowire level. Okay? And of course, when we're dealing with semiconductors, heterojunctions, everything, okay? In the sort of conventional semiconductor industry, PN junction, the heterojunction is everything for LED, solar panel we talk about. So this is something we need to do as well. We establish all these different techniques by modify the sort of the CVD process, chemical vapor deposition process. You can make vertical junctions. We call this longitudinal junction. You can make core-shell junctions. Those are the different sort of heterojunctions that enables us to explore, for example, their optical properties and the thermal properties. Okay. And with that sort of precise control, later on, I think since 2000, over the last more than 20 years, this field is just exploded with many research groups basically making progress in many of these sub-areas. Okay? In the photonics area, lots of groups are working on the electron transport, making transistors, thermoelectrics, and lots of energy storage study as well, and all the way to artificial photosynthesis. I will basically use these three as the example to illustrate the impact of these one-dimensional semiconductor nanostructures in the photonics area and in the thermoelectrics and also solar field directions. Okay? And just 5 years ago, we worked with David Ginger at Chemical Review, put together this comprehensive review for the field, 25 years research on these one-dimensional nanostructures. Okay, so let me start with the first topic. It's related to the nanowire-based photonics. And one of the major sort of first development in this area is observation of lasing in a nanoscopic cavity. Okay? And this is really taking advantage of the single crystalline 3,5 compound, or 2,6, okay, zinc oxide or gallium nitride, and then later on, like Lars Samuelson's group at Lund University expanded into sort of more traditional 3,5 compound as well. You will see these nanowires are basically cylindrical. They are single domain, okay? And their end facet is hexagonal, okay, because of in this case, zinc oxide or gallium nitride have the Woodside structure. So typically they are hexagonal. Cross-section is 100 nanometer. And of course, initially when we look at these lasing phenomena here, there are two layers of these are the sort of optical spectra, the different optical pumping, and this is the emission speckle. You can see that's typical behavior of these coherent irradiation from the end facet of these nanowires. And of course, back then when we were talking about this, it's basically not known that the laser cavity can be that small, because this cross-section is already below the wavelengths we're talking about. It's sub-wavelengths. Okay? And indeed, that's possible. And that's, again, related to, again, the end facet is atomically flat. They have high refractive index. Okay? That helps in terms of the overall optical confinement within these nanoscopic cylinders. And this same idea, using these nanoscopic cylinder as a laser cavity, again, has been extended by many other research groups from UV lasing all the way to near IR lasing. Okay? And certainly we spend quite an amount of time to looking at the single nanowire cavity, looking at their sort of optical pumping at different intensity, looking at the threshold behavior, extended to, for example, gallium nitride system. Okay? And this is, again, similar sort of single nanoscopic cylinder. Okay? And all the way to, as I mentioned, this core shell structure. This core shell structure is essentially a gallium nitride quantum wires, couple of nanometers in dimension. Okay? It's a quantum wire of gallium nitride. And its shells, the shells is the aluminum gallium nitride, the large dielectric index. Okay? And the whole cavity basically is essentially, you can consider it's a quantum wire laser out of this gallium nitride. Okay? That's also possible. And of course, you notice that when we're looking at these single nanowire lasing, these are all optically pumping. And you will see actually at above lasing threshold, they have multiple sort of modes. Okay? And that's basically is dictated by these laser cavity. You can basically engineer it a little bit. Okay? If you have a cleaved, this so-called cleaved coupled cavity, two laser cavity with different cavity lengths, then you can pick which cavity mode you are going to amplify. Okay? Eventually, you can get it to the single mode operation. Okay? And that's can be done easily now with sort of precise control of these nanoscopic cavity. Okay. And of course, that's optical pumping. Okay. You can basically make all these single crystal nanocavities and demonstrate optical pumping at different wavelengths. Okay. And for the community to move forward, we need electric injection. Okay. And that's basically, later on, I led a DARPA program with a couple of my colleagues at Berkeley and also at Illinois. And that leads into the basically electric injection laser, okay, metal, basically the metal cavity coated cylinder. In this case is a 3,5, okay, 3,5 compound in the sort of in the visible region. Okay, and so this is something that from the optical pumping all the way to electric injection nowadays it's durable. Certainly now there are companies are working on scaling this thing up for display purpose. Okay? And that's already sort of slowly entering into the commercial market, especially in the display industry. Okay? Here's one movie. These nanowires are very flexible. Okay? And I want to show this movie because this illustrates another unique mechanical properties of these nanowires. Usually, the semiconductor, if you bend like this, they will fracture. Okay? And another major benefit of these single crystal semiconductor nanowires is the dislocation. You can remove the dislocation from these single crystal nanowires, therefore they don't easily fracture. Okay? So this is one sort of a small story on the sort of making nanoscopic coherent light source out of these one-dimensional single crystal nanowires. And I think eventually they will have major applications. For example, in the photonic integrated circuits, in many of these things we're nowadays also doing is delivering an imaging on single cell level because they are very flexible. They can use that as a point source, point delivery source and a point light source as well. Okay. Okay. So that's the first part on the sort of very briefly on that nanophotonic story. Let me move on to the second part. This is about the getting back to the size control. Okay? At the very beginning, I mentioned when we talk about these nanowires, it's basically they are confined in 2 dimensions, the cross section. Okay? What is they certainly behave as a very nice nanoscopic laser cavity. And what happened to the electron transport? What happened to the other sort of particle transport, like the phonon transport? Okay, that actually is getting to the sort of the size control that can tell us something very, very interesting. And this goes back to a prediction by Millie Dresshauser back in '93. Okay? In this paper, Physical Review B in '93, Millie basically predict actually if anybody can make a semiconductor nanowire down to nanometer scale, you will see something very interesting. At the very beginning, I mentioned the one-dimensional sort of electronic system have very special density of states, the singularity near the Fermi surface. And that will enhance the Seebeck coefficient for the sort of thermoelectric community, this one. Okay? Meantime, Millie also predicted that when you drive these one-dimensional nanostructure down to smaller scale, you are going to block the phonon transport, which is thermal transport. Okay? So this is basically the thermal conductivity of semiconductors here, and the Seebeck coefficient is over here. We can call this as a power factor. And that basically is this formula, ZT, is telling you how efficient a thermoelectric material can be used to recover waste heat. Okay? In the thermoelectric community, the people are really trying to improve this ZT factor so that the energy conversion efficiency can be much higher. Okay? So Millie basically theoretically predicted back in '93, and it's basically after 10 years, I worked with my colleague, Arun Majumdar. Arun now moved to Stanford. Okay, really for the first time to figure out quantitatively to measure the size-dependent thermal conductivity. Okay? And this is the platform where suspended these individual nanowires in a sort of local microbeam. You can heat on one end, measure the thermal heat through the thermal bridge. Okay? Then you can calculate the thermal conductance of this single sort of silicon nanowire bridge. And then again, you can measure these silicon nanowire bridge in terms of their thermal conductivity as function of the size, the diameter. Okay? You are seeing here is like 100 nanometer all the way down to 20 nanometer. Okay? You will see, first of all, of course, this is temperature-dependent thermal conductivity, right? Thermal conductivity, you can see it's going down, okay? As we drive the size of these nanowires, okay? Let me just put as a reference, the bulk silicon is a very good thermal conductor. It's basically, it's somewhere here. At the room temperature is 300 watts per meter Kelvin. It's somewhere here, okay? So when you are working with silicon nanowire, you can see thermal conductivity is significant decrease below even 10 watts per meter Kelvin. This is not surprising. Okay? Certainly, Millis actually predicted that early on. Nowadays, when we look at our sort of cell phone, okay, very shortly you will see it's heating up. Okay? That's because we're packing too many of these small transistors there. The silicon, nowadays, silicon transistors getting down to sub-5 nanometer node. Silicon is at a sub-5 nanometer node. Electron transport is no problem, but it's becoming a thermal insulator. Okay, so that's why our sort of cell phone, laptop can be easily heat up. So silicon, once you're getting down to nanometer scale, it's still can function perfectly as transistor down to, I think now the semiconductor industry can drive down to 2 nanometer level, okay? But thermally, that simply cannot handle it. But meantime, that offers new opportunities, of course, okay? So in this case, in the vertical junction, you can further putting this silicon germanium vertical sort of longitudinal junction. That's another way to block the photon transport, okay? You can drive the thermal conductivity further down, okay? Why we want to drive in this case, drive the thermal conductivity sort of down? That again relate to the thermoelectrics. Okay? Eventually, we figure out a way actually larger scale production with these silicon nanowires. Now, with this sort of photon transport or photon engineering with this nanoscopic dimensionality, the silicon nanowire in terms of ZT can be enhanced at 100-fold compared to bulk silicon. As I mentioned, bulk silicon is a thermal conductor. It's not a good traditionally not considered as a good thermal electrical material. But here, basically, this low-dimensional silicon nanostructure offers a sort of a potential to make low-cost thermoelectric material that can recover waste heat. Okay? And that was basically eventually leads into a startup, Alpha Energy, that scales everything up. And these thermoelectric sort of energy conversion, you can convert waste heat into electricity. Okay? Typically, these sort of thermoelectric generator, you can recover 2 to 3% of electricity from the waste heat. Okay. Okay. So that's the second story on sort of the size-dependent thermal conductivity of these one-dimensional nanostructures that leads into development of a new type of thermoelectric material. Then the last part I want to share with you is our more sort of our recent efforts on utilizing these high surface area semiconductor nanowire as photoelectrodes to drive the CO2 fixation using sunlight. Okay? And this is basically with the motivation to develop an artificial photosynthetic system to drive the carbon dioxide back into, store basically solar energy back into the carbon-carbon bond in one sort of integrated system. Okay? And again, the basic concept we are taking is so-called this photochemical diode. Okay? And this basic concept was proposed by Arnold at Unreal. Again, it's very earlier. It's back in the 70s. Okay? Within this, fundamentally, within this photochemical diode, you have two types of semiconductor, a P-type semiconductor, N-type semiconductor, and then in between them, there's ohmic contact. So this sort of photochemical diode is very different from the PN junction we talk about for solar cell, for LED. Okay? The in between the P and N, that's ohmic contact, then you place this junction into electrolytes, okay? And one side Okay, of course, Arthur Nozick initially proposed this idea for solar-driven water spreading. One side is hydrogen production, another side is oxygen evolution. Okay? So this concept, again, was proposed back in the 70s. However, in order to demonstrate this concept, it's also very difficult in sort of single-pass, optical pass scheme. Again, back then, you can see the scheme of things. It's millimeter scale or even centimeter scale. So it's almost impossible for the light going from one photocathode to anode, right? So, but that can be easily resolved with the latest development of this dimensionality controller nanostructure. So we actually introduced this sort of revised this original bulk design of photochemical diode using basically by incorporating this sort of high surface area nanowire array in this Helios program. Okay, that's back when Steve was the lab director in 2003 or 2004. You can see this is essentially in terms of the electronic structure or band alignment is similar to Arthur Nozick's original design. However, now it will reduce down to this sort of millings of these nanoscopic photochemical diode made out of these nanowire photocathode, nanowire photoanode. And then they basically linked everything together. The overall is still two photons goes in. Okay? One photon activated the photocathode, another photon activated the photoanode. Then these electron or holes, those are minority carry from two types of semiconductor, migrate to the surface to drive water reduction to producing hydrogen or CO2 reduction to producing carbon-carbon bond. Another side is water oxidation to give you oxygen. Okay? And this sort of design later on was propagated into the energy hub, JCAP1 and 2. And now the phase 3, LISA, is still ongoing. We'll still continue push actually with some revision of the original design. Okay? Okay, why the nanowire photocathode or photoanode? Okay, just two very quick reasons behind that. One is basically the high surface area, and they can orthogonal light absorption and charge migration. Okay, and that's the single crystalline channel can give you. And the second is matching the solar flux with catalytic turnover. Okay, these are based on the single nanowire photoelectrochemical measurement. You can measure actually how many electrons and the one-sign irradiation you can extract to the surface to do chemistry so that electron flux can match with the turnover frequency of the catalyst you put on the surface. Okay? And that basically these high surface area nanowire give you this advantage. Okay? And these are the typical sort of photocathodes. They have light trapping phenomena. Light goes in. They cannot escape until they be absorbed. So that's the unique sort of feature of these high-density nanowire array. Very high surface area. You can decorate them with all sorts of different catalysts you can develop in your lab. And notice actually the photocurrent density. I think this morning in Michael's talk, in one sound condition, you can easily generate 20, 30 milliamp per square centimeter in terms of the electron flux you can do chemistry. Okay? Now, if you start to putting together these nanowire photochemical diode, you can run the water spreading, okay, by combining P-type semiconductor, N-type semiconductor. And this so-called, this cross point is the sort of bias-free operating current density. Okay? We can do it in the typically sub 5 milliamp per square centimeter to generate oxygen and hydrogen. And in this case, basically, you have the photo voltages supply the thermodynamic voltage you need for water spreading, okay, the 1.23 eV, okay, plus all the overpotentials. Okay? That's durable. However, if you want to do CO2 reduction, imagine you put the CO2 catalyst on the surface, we have one issue. CO2 reduction, we don't have a good catalyst with very low overpotential. You need to waste 1 volt to drive CO2 to C2. Okay, then our photo voltage is not enough. Okay, so this basically gives essentially it gives us a little bit sort of very challenging requirement how to resolve this overpotential issue for the CO2 reduction. Okay, and that's basically how to overcome this photo voltage gap. Okay, to drive the CO2 reduction. Okay, and at that time basically we started to basically introduced from the abiotic CO2 reduction using, for example, using copper or those metal nanoparticles because their overpotential is too high. We basically transform into a basically bio-based CO2 reduction. Okay, it turns out in nature there are these microorganisms can run CO2 chemistry with minimum overpotential, 200 millivolts, CO2 to C2 product. Okay? And that's something we start to introduce into the system. That basically end up with the first nanowire-based biophotochemical diode and the bias-free operation condition. No external energy goes in. So what happened is basically optically excited nanowires provide electron to these microorganisms. Okay? Within these microorganisms, we have this acetyl-CoA pathway. And in this particular example, of course, the electron generated from the semiconductor is serving as a reducing equivalent that propagating into this biological system as other reducing equivalent like ferrodoxin, reducer ferrodoxin, NADH, NADPH. They enter into this acetyl-CoA pathway, eventually fix CO2 into, in this case, is acetate with almost close to unity selectivity, yet with the overpotential only 200 millivolts. Okay? So this is much superb sort of catalyst for CO2 reduction compared to the synthetic system. Okay? So Liu basically developed this fully integrated system. One side is water oxidation, another side is CO2 reduction. Essentially, one sun irradiation, CO2 goes in, goes to 100%, goes to acetate. Another side is the water, oxygen is coming out. Now, once you fix the CO2 into acetate, then you can further upgrade the acetate, in this case, into other sort of chemicals, liquid fuel like butanol, biodegradable polymers, or even chiral species in this drug intermediates. Okay? But now all of these, basically the whole system operate under one sun irradiation, no any other external energy input. Okay? And all these carbon now is coming from CO2. Okay? So that's the first version, sort of in really first version of bias-free operation of CO2 fixation using this nanowire photochemical diode. Okay? And then later on, we can basically optimize everything, getting down to sort of 4% of solar to chemical energy conversion efficiency. I think, how much time do, 1 minute? Yeah. Okay, so very quickly, I talked about OER side, water oxidation on the photoanode side. Okay? We know that OER side is sluggish, it is energy demanding. Okay? So more recently within LISA, we're actually starting to revise the nanowire photochemical diode by replacing the OER with another organic oxidation reaction. The moment you remove the OER from this equation, you essentially remove the 1.3 volts from the sort of voltage needs. Essentially, one side you are fixing CO2, turn that into carbon-carbon bond. Another side you are oxidizing certain organics and producing also useful chemicals. That leads us to basically this new version of the nanowire-based photochemical diode. And this time, actually, both sides, cathode and anode, are silicon-based. So this photochemical diode can be powered directly by red light only. Okay? You don't need sort of short wavelengths. Red light is enough to operate this. You can run this at now, if you are using silicon nanowire, you can do this in the 6-inch wafer. So now we can actually readily do this sort of a bias-free operation at slightly below 10 milliamp per square centimeter to drive the CO2 fixation or drive the water splitting into hydrogen. And the other end, you can do the sort of replaced by the glycerol oxidation. Okay, that gives you another useful chemical product as well. Okay. So on the nanowire photochemical diode side, I think it's also will also make some progress that they really can do the bias-free operation just as Arnold early on predicted. We can run that in CO2 fixation. Now at bias-free condition, close to 10 milliamp per square centimeter. Okay, that's the and plus this can be red light powered, so that way potentially we can operate this 24/7 instead of waiting for the sun irradiation. Okay. And with that, I think I'm going to close. by saying that back in 20 years ago, we had this foundational nanowire IP that initially covered everything in terms of heterostructure, different size control. That initially was licensed to Nanosys to develop this system, later on spin off as another company as 1D. Nowadays, this 1D actually company is scaling up this silane-based chemical vapor deposition system to produce these nanowires in 100 tons per year. Okay, mainly they are supplying to EV industry to make batteries. Okay. With that, I want to conclude that essentially I work through this my personal, almost personal 30 years of journey in this nanowire research. I want to thank my whole group over these more than 20 years of work, and also founding agency for support this work. Thank you for the invitation.
Thank you, Peidong Yang. We have time for a couple questions.
Thanks, Peidong. It's a real splendid lecture. I just wondered with your membrane system, you need a proton transfer across the membrane, otherwise you cannot scale up. So how do you solve that?
Yeah, right now we are still using the bipolar membrane in this, whether we are doing the solar-driven water spreading or CO2 reduction. So in the device we are dealing with nowadays, I think it's a 3-inch device, kept sitting in parallel. Then in the middle, that's the bipolar membrane. So 3-inch wafer scale, especially in the last example, red light powered, it's okay. I don't know how much we can push that. We want to push to 6-inch wafer operation. Then the membrane probably becoming an issue, because you need the proton goes from one side to another. Okay. When the area is getting larger. Yeah. Great question.
Time for one more question. All right, if not, then let's take this moment to thank all of our speakers and Peidong Yang once more. And that concludes the second session for today. Thank you all.